All right, let's dive right into this explainer and decode the literal mechanics behind one of Earth's most explosive phenomena. Volcanoes are absolutely awe-inspiring, right? Sometimes terrifying, but totally essential to understanding how our planet actually works. But how do they do what they do? We're going to break down the hard science and see exactly what's brewing right beneath our feet.
Seriously, to understand the sheer power of a volcano, just picture a shaken soda bottle. You've got liquid and gas completely trapped, building up this intense pressure against the plastic. And the second that cap opens, boom, total depressurization and a violent, uncontrollable spray. It's something we've all seen, but honestly, it is the perfect model for the mechanics happening deep underground.
Which begs the question, what exactly is the Earth's version of a shaken soda? Well, we definitely aren't dealing with carbonated water here. We're talking about forces that are exponentially more powerful, materials that are infinitely hotter, and a pressure chamber that literally spans thousands of miles.
Section 1. Earth's giant soda bottle, understanding molten rock and pressure.
So, before anything even comes close to erupting, extreme heat and pressure create this molten rock deep below the surface, which we call magma. Now, solid rock doesn't just melt on a whim. It takes extreme heat, huge shifts in pressure, or water actually seeping in to lower the rock's melting point. When all those factors perfectly align, solid Earth transforms into this thick, churning liquid.
And here's a fun distinction. The name totally hinges on location. As long as that molten rock is trapped deep underground, hiding out in the dark, it's magma. But the literal second it breaches the Earth's surface, we call it lava. It's the exact same fundamental material, you know? Magma is inside the bottle, lava is what spills out.
Section 2. Magma and plate boundaries. Where do volcanoes come from?
Volcanoes generally pop up in 3 distinct zones, all driven by shifting tectonic plates. First, you've got convergent boundaries, like the Andes, where a sinking plate actually creates magma that rises up into these towering peaks. Then, at divergent boundaries, plates are pulling apart, letting magma slip right up through the massive cracks. That's exactly how Iceland was built. And finally, hotspots, like Hawaii. These are independent, super deep magma plumes that just rise up entirely on their own, completely ignoring plate boundaries.
Section 3. Volcano anatomy and types. The design of the bottle.
No matter the type, every volcano shares the same basic plumbing system. Way down deep sits the magma chamber. That's your main storage tank. When the pressure gets to be too much, the magma forces its way up through the vent, which is the main vertical pipe right up to the crater at the summit. Once it finally bursts through that top opening, it turns into a lava flow moving down the mountain.
Now, the type of lava actually dictates the physical shape of the mountain itself. Runny lava spreads out super fast before it cools, which creates the really broad, gentle slopes of a shield volcano like Mauna Loa. On the flip side, if you have alternating layers of thick ash and lava, you get those tall, classic, highly explosive peaks of a composite volcano like Mount Fuji. And then you have cinder cones. These are much smaller but incredibly steep, built entirely from fragmented volcanic materials piling up rapidly around the vent.
Section 4. The eruption trigger, the pop.
Okay, this next simple fact is the absolute key to the whole process. Magma contains dissolved gases. It is not just liquid rock down there. There are immense quantities of gas bubbling within that fluid, and they're only kept trapped and dissolved because of the crushing weight of the Earth pushing down on them.
So watch how this chain reaction plays out. As the magma starts to rise toward the surface, that immense downward pressure naturally drops. With all that physical weight lifted, the trapped dissolved gases are suddenly free to expand rapidly. They suddenly take up vastly more space, and that creates an unstoppable upward force that ultimately blasts the magma right out of the mountain. Pop goes the cap.
Section 5. Why volcanoes matter. The aftermath.
Of course, we have to recognize the absolutely severe, destructive forces unleashed during an eruption. Lava flows will literally consume everything in their path. Massive ash clouds can completely blot out the sun and ground flights for thousands of miles. You've got deadly, fast-moving avalanches of hot gas and rock, called pyroclastic flows, sweeping down the slopes, and massive eruptions can even alter the global climate by throwing huge amounts of debris into the atmosphere. But here is the really fascinating plot twist. These terrifying eruptions are also massive engines of creation. That choking volcanic ash, it eventually breaks down into some of the most incredibly fertile agricultural soil on the entire planet. Lava cooling in the ocean expands coastlines and forms brand new land right before our eyes. Plus, that intense, shallow heat provides us with vast reserves of clean geothermal energy.
Boiling the whole shebang down, our planet basically vents its energy through a very simple equation. Heat plus magma plus gas pressure equals Earth's pressure release system. An eruption is really just the mathematical sum of immense subterranean heat the molten rocket creates and the explosive pressure of those expanding gases finally finding an exit.
So, volcanoes are Earth's way of releasing the enormous heat hidden deep inside the planet. Next time you crack open a soda, keep that in mind. Remember those massive forces constantly at work right beneath your feet. They are a necessary, awe-inspiring function of a dynamic, living world. So, as you feel the solid ground beneath you today, ask yourself, just how much pressure is building up right now, miles below your shoes, waiting for its big chance to burst to the surface?